You might recall when we were doing the first few classes, we talked about level clusters in molecular rotors. And today we're going to show the simplest examples of that in band theory of one-dimensional lattice.
Oh, okay.
We've essentially already solved that for a very simple case where we have a lattice of three potential wells, which acts like three-atom lattice, and it's in a ring, so it's a one that satisfies periodic boundary conditions. And the picture of that is on the first slide to the right. Today, we're going to relook at that as an analog between that, which was obtained by a quantum H matrix, and what you would get if you had simply a vibrating triatomic molecule that had a K matrix. So this is classical physics, that's quantum physics, but we're using the same sort of symmetry algebra and notation for both of them. So that is the main topic of the first part of this lecture, and the molecular K matrix construction is very different from what you do to make a quantum H matrix. But in any case, once you have that, then the local to global symmetry arguments carry for the classical vibrations. The local symmetry that comes out of a cyclic 3 instead of a cyclic 2, that is reflection symmetry, and then this is a moving wave C-type motion that molecules have to eventually obey because the molecules are rotating and the vibrations are having a Coriolis effect. Now the algebra of what we're going to be doing here is the difference between going from a large group, in this case D3, and a small group, in this case C2, or C3, either one of those. We call this subduction or splitting. And the other way, when you make a table for this and read it backwards, that's the one that gives you the clusters for the rotational spectra, and in our case gives you the tight bands when you have really deep potentials and the local symmetry takes over. So this is our first look at the mathematics behind that, which has a famous mathematician's name in it. It's called the Frobenius reciprocity axiom, theorem, whatever you want to call it. Now finally, after we do that, we're going to look at a little bigger symmetry, D6, hexagonal. Not a thing to worry about because all we do is take D3 and cross it with C2 and produce all the characters and immediately have the band theory from that based on what we're doing first today. So that's just a rundown of this. Again, the reference page is always page 2, and every one of the table of contents for each of the sections should have a link to page 2 so that you can quickly go get links, and then we're going to work on how do you get back to where you were. That's another issue. But we're getting modern here, as you can see. So anyway, quick review. This is the matrix analysis that we did for the H matrices. For the triple well, D3 symmetric wave functions, tunneling wave functions, if you will, because if the barriers are high, you call any interaction between the separate wells tunneling. And that's when the local symmetry is in effect. And that's what we need to discuss more about today. So this was the very last thing, which I just realized I haven't linked this, but you know where it is. It's at the end of the previous lecture. Okay, and then the picture of the bands that you get by using that theory. Now, here we're going to go to classical resonators. And I should really it's quite true that every one of our high-level quantum field theories begins with a classical equation. That is just a part of our work, especially in atomic and molecular physics. So what we're doing here is we create a classical equation, and then we quantize that in the sense of turning the oscillators that we get for each of the modes into a field theory. So the A daggers and all of that come for each of the modes that come from looking at this equation here with a K matrix and a time derivative that is squared. So this is mass times acceleration, and we put minus sign over here because that would make this a stable oscillator. The K matrix is this, and we've seen this already. And also I think that I point out early on here these two links take us back to our U2 versus R3, Schrodinger versus classical oscillator, two-dimensional oscillator, which is really what I'm talking about here when I say the classics comes first, the quantum second, still at the deepest levels of much of our physics. Now this paper right here is another link, and you'll find more about this. In fact, these texts come out of that paper. And you see we're comparing here Schrodinger's equation for quantum motion, which has a single derivative. So essentially, the square of this equation is this equation. Remember that argument that came at the very end of our discussion in lecture 4.
Dr. Hardy?
Yes.
What is that part?
This is your spring constant matrix. So this is the Hooke law constants, and this is generalized Hooke's law for the distortion of an oscillator from its equilibrium position. So basically, if this was a one-dimensional oscillator, it'd be Kx.
Oh, so that's a multi-dimensional oscillator?
And this would be the partial derivative of a potential 1/2 Kx squared. But now we're doing basically Lagrange's equations. And then this right here is the acceleration. So mass times acceleration is equal to force, Kx. So this is Newton-Hooke. Remember? The two guys that hate each other so much, but they live together now in our eternity. They're together now.
I mean, I was asking because I have seen like sometimes when you have like these problems, you like set up a matrix, and it's like a Hamiltonian for the system of springs, and in the
that's exactly what this is. That's what we're doing here.
Like depending on the symmetry of the spring, you have like the K's in the corners, like the K's in the diagonal, or something like that.
The question is, how do you get those K's? And I've got a new thing that we're pushing right now for doing that. But I'll show you the old one too, just to keep it right. But a lot of this is in the quantum theory, but most of it's in the classical stuff is in the classical book, Classical Mechanics with a Bang. So we squared this, blah, blah, blah. That's the equation. And then remember that the eigenvalues that we get from a K matrix are the squares of the frequencies. The Hamiltonian H matrix eigenvalues are the basic frequencies of the phase of the quantum system. So squared, keep that in mind. Hooke's law, Km over omega, Kn over m is omega squared, just for a single oscillating mass. And apart from normalization eigenvectors of H and K, eigenvectors of these two are the same. So we get to make an analog with our triatomic vibrating and rotating molecule with the band theory of the H matrix that we did in the last lecture. Okay, so each eigenvalue corresponds to its respective energy spectrum, but what does that mean? What we really mean is that we're going to be mixing the modes and looking at the beats. Okay, so we got a potential here that's a sum, and we're using Dirac notation now for classical system. I think we started off when we discussed CN symmetry with just exactly that. And each K component is a sum over spring constants that connect, say, a coordinate axis, perhaps a Cartesian coordinate axis, that's what we'll use here all the time, and some other axis. And then it's multiplied by a factor that are the two dot products, that's the direction cosines, basically, of the spring to the coordinates, and typically. And this is the thing that's new here. Instead of just direct connecting to nuclei of a polyatomic molecule, we ask the question, well, if I move this thing, say, in this direction, or in this direction, or in that direction, you see, what's the direction that the force shows up here? Is it really in the direction of the spring connecting it if you draw a straight line between the things? Well, no. It's probably better to imagine in general some kind of curve, say a circle to start off with, that has a radius ranging from infinity, which would be a straight line, and some other value, or a negative value even, where it goes like that. So this opens up the possibility for getting better parameters for polyatomic vibrations. We won't use it much here, but we will use the formalism to describe that. So we're going to have coupling between a nucleus A and a nucleus B that has, and it's shown here, just two coordinates. But when we do SF6 molecule, we're going to have three coordinates for each nucleus, and then the springs are imagined to be between those. And in all of the stuff that I've written so far, we use straight, direct springs. But I think that's going to change now. Anyway, that's this is the basic idea of the formulas again, the KAB matrix. But we also have to worry about the self-energy. They're the diagonal components. These guys right here, where A equal B. But in general, there are more connections. You have N, N nuclei. You have something like N times N minus 1 over 2 connectors, but you only have N of the cases where A is equal to B, the same nucleus just feeling its own self-springiness. So that's the formula that comes out of this, and the dot product, the direction cosines, are the geometry of the springiness. Something we don't worry about with tunneling. Tunneling just tunnels in a direct way, and we rarely have to worry about that. So considering a triatomic, which is what we're doing here, these are possibilities. These are the way I'm setting the parameters. Having more parameters than just one spring constant, there are a whole bunch of things. And the other thing that we're going to do is we're going to actually have this free polyatomic molecule get nailed down. So they're going to be little groundings, little springs that are actually attached to some frame, so that this molecule will not be able to freely translate, but we'll use such small values for these springs to couple it to the frame that the translation will be really low frequency, you see. And the rotation, it will also rotate, but it'll have a libration instead of a simple rotation that goes forever. So this is just in order to get all of the modes, including the ones that are called non-genuine. That includes the translation degrees of freedom and the rotation degrees of freedom. Okay, so let's go with that in here.
Yeah.
That's the one we'll solve last. We'll do this one first, because we have already the answer to that.
The second line after the second paragraph. Yeah. The second line after the second paragraph. One up.
Oh, this one?
Yeah. So, del L K.
Yeah, the delta of the length due to a distortion. That's what we're thinking. So we call 0 for this when every nucleus is sitting on its equilibrium position, wherever that is. Okay?
That's KB dotted.
Anytime you do one of these, but in other words, every time one of these goes non-zero, then the molecule, like you just go with a thing, is sitting there happy to be that, right? It won't move if you let it go, okay? but then you go like this, right? And as soon as you pull one of them off center, the whole molecule is going to be feeling force, right? They're all going to start to move, right? In a very complicated way, because you've just made a linear combination of all the normal modes probably, by just moving one, right? Just like when you move one wave function of an eigen state, right? Somehow you go in there and put more amplitude there, right? All of a sudden, all of the eigenfunctions now will start to move. You'll have been given them non-zero amplitude.
Yeah, that's why I'm having.
That's what's going on there.
Yeah, but I'm having trouble visualizing like how that delta LK squared equals that summation of over A and B.
Right.
I
right.
don't.
We'll take some. Maybe it'll help to just look at what we write down for this. In this case is the old-fashioned one. But you have to sum over these terms as well as these. Okay. So this one right here is basically the sum of all of the delta LKs that you can possibly imagine having.
Okay. Now, okay, I understand now.
Does that make a little bit of sense?
It's because like the representation you were using just that. I said like, well,
This is really what you're trying to write, right? You're trying to write this guy, right? So you've got a whole bunch of sums over nuclear coordinates. In this case, we got 3 guys that can move in a plane, so we've got 6-dimensional matrix here.
that.
The K matrix. Yeah, this is K operator to make the matrix. Yeah.
Okay.
An example I think will help, although we're going to do the more complicated arrangement of springs first, because remember, if this thing has the D3 symmetry, we only need to write the top row of the K matrix, right? That's cool, right? And that top row has these parameters, which are each labeled by the group operators that get you to that particular position in the matrix. So that you know, it's the same deal as far as the matrix goes as it was for the tunneling matrix in the Hamilton of the quantum problem. Okay. So the first row of parameters, 1, K, GB, remember that's what the group theory then takes, that's what it then uses, those numbers to give us eigenstates and eigenvalues in terms of parameters that we have in 6 of them here. Possibly complex. These 2 can be complex. These can't, because they're associated with C2 symmetry. It has no possibility of being anything but 0 and pi in phase. Okay, so what we have with this arrangement is 3 spring constants. Well, 4 if you count the K0, which is just the one that's kind of holding the thing at the spring goes to the points toward the center there. But then the R and the one that goes with I3 and so forth, it's just a matter of looking at each of these and using that formula to write down something to go in these parameters. These 6 parameters are then related to this, whatever it is, the model that you've made. Now I picked a pretty complicated model right there, but so be it. And that is the geometry of this thing. Now, we already looked at a matrix like that. That is, we looked at this particular problem right here, where the very first row was just those numbers, R and I, 2 and sub 2 and 1 for the R's, sub 1, 2, 3 for the I's. That has been replaced by the K's, the actual springs that make up this particular mechanism that has the curved springs. And the result of this, which we will compare here to the result of that, consists of projectors, XX, YX. Now, those are written a little small here, but they're bigger over there on that screen. That go with the E representation of D3, the doubly degenerate representation. And then the very first one, the ground here, is A1XX. Now, these aren't necessarily in the order they come, and so as a matter of fact, the way these springs work, this whole thing gets turned upside down. So this ends up being our highest frequency. This one right here ends up being actually 0 frequency if we don't connect it to the laboratory. So this one, as you can see, is just rotation. Whereas here, it's the highest frequency because it has the most nodes, and that's what counts in quantum mechanics. Here it's, what sort of springs are you using to hold this thing that determines the frequency. So we'll see this as upside down. We'll see some animations of this later on here. But in any case, what it means to be XX, that means symmetric globally and symmetric locally. What that means, and if I can just for a moment here point to this example here, which we've talked about, this was the one of the E degenerate states that had symmetry. That is, was symmetry globally, which meant that this plane, the master plane, it was symmetric. These had the same sign. Black and black, okay, is the same. Whereas this one over here is quite the opposite. This one has a global anti-symmetry, but also has local anti-symmetry. The waves inside each of the localities is anti-symmetric. So is this one. These two come as a pair. The local symmetry is Y for both of them, but the global symmetry is X, symmetric for this one and anti-symmetric for this one. And same for here. This one, the global symmetry is symmetric for the X in the global spot and anti-symmetric with the Y. You can see this is black versus red having a negative phase, this a positive phase, so anti across there. But locally, both of these, the second index, is symmetric. Okay, they both are symmetric waves that have no node in the center. Even though I've drawn it with a little dip there, that would be a smooth wave inside the well there. Okay, that you see over here. Okay, you see those are all just Gaussian-like waves with no nodes. Whereas the next set of levels here, these two that are degenerate and this one up here, are anti-symmetric, and this one is really anti-symmetric. So having a YY in it, kind of like that one has, but this one makes it way up even higher because of the arrangements. The tunneling is making that energy is making that one higher. Okay, so this one analogous to that one, and so forth. So that's kind of a stretched analogy. This is a bunch of bed springs, and that's some really tiny little quantum mechanics going on in some sort of nano circuit, okay, or nano band, right? And there's a big clunker here, okay? So that's a stretch, right? That's the biggest stretch in analogy. But when you're doing it with symmetry, you use the same for both. So it's very good mathematical analogy. At the least. Okay, there it is again. All right, now let's go ahead and look at a direct connection, because that's what if you go to a book that has a study of the simplest triatomic molecular system, the simplest model for ozone molecule, oxygen 3. Okay, which is not a stable molecule. And it's what you smell after a very bad thunderstorm, or very good, depending on how much you like the weather to go crazy. After a very good thunderstorm, if you go out and a couple of lightning strikes in the neighborhood, you'll smell the ozone. But if you just go into your physics lab and turn on a Van de Graaff generator and run it for a while, you're going to smell the ozone too. Okay, it's a terrible poison, but you're already smelling parts per hundreds million. Parts per 100 million. It's enough to you can smell it. You get down to parts per thousand, you better watch out because it is very poisonous. So don't get a tank of ozone. Well, if you have a tank of ozone, you have a bomb, basically.
So what does
A lot of
lightning,
oxygen.
what does thunderstorm do, Dr. Does it ionize the atmosphere?
Yeah.
Okay.
It pulls the oxygen 2 apart, but then you see you have a bunch of oxygen 2s that are looking to get back together again. Every once in a while, they get together to form O3.
Okay.
And that lasts for a while. And you go, and you take a few of them in. Yeah. Interesting chemistry. Okay. So ozone is, and most of the molecules of polyatomic that have D3 symmetry are not stable. It's not a good arrangement. But some last longer than others. Anyway, with a direct connection, this is the actual angles that direct connection makes. The 75-degree angle there between this coordinate, the number 1 coordinate, and the connection to number 2 up here, and so forth. Those are all necessary. And the cosine of 15 and 75 are numbers that kind of weird. 2 plus or minus square root of 3. Okay, so this is different from the quantum mechanics. In the quantum mechanics, we just have a parameter S or something like that. Here, we actually think we could make something out of the spring constants, and the spring constants, chemists will give you the spring constants. They don't call them that, but the force constants of a molecule, and you can see how well you can reproduce the vibrational spectra of that molecule, and that's what we've been doing with the big polyatomics, or at least trying to do it. It's not something that gets you more than about. You're really happy if you get 2-figure accuracy. Most of the time it's 1 figure. Okay, so that's the matrix that we need to solve in terms of the constant K1. We've only got one constant here. This one, as it's shown, is not attached to the laboratory. We're going to do an animation of one that is. But there's the matrix down there. 3K over 4 in all positions. Now this is a matrix that does not respect local symmetry. As a matter of fact, it goes at local symmetry. Global and local get mixed 50-50 in this example. So that I want to show first off with this thing. In other words, these are the eigenvectors of this matrix. Plus and minus 1, 1, 1 minus 1. I mean, it's an idempotent matrix, right? C2 symmetry with no argument about it. So I get a plus and minus the states x and y that the group theory gives you with the standing wave eigenstate. So result is a frequency of 3k over 2, presumably divided by mass. We're taking that to be 1 here. So 3k over 2 and 0. Well, there has to be, because you have to realize that we've got a translation mode that consists of 2 dimensions. And we also have rotation, which consists of just 1 dimension. We're all in a plane here. So these are the way the modes actually look. And if you take the modes that we got from the preceding slide and do the addition and subtraction, for instance, if you take the XX and add XY, so there's a 50-50 mixture of symmetry and anti-symmetry locally. Remember, the second index is the local guide, okay? When I add those two, what I get is what you see right here, the sum here of the modes that we had before, and I might as well put them on the other slide just so we can make a reference to these guys. This would be this slide right there. So I'm taking those modes for the E's and doing a plus and minus. Okay, here's where I add local symmetry and anti-symmetry. And I do it here again. This doesn't have a pair to go with it, so it's the same. And it happens to be up there. Now it's down here. This is a low frequency mode. Then comes this guy right here. Now look what it is. This one is just translation. So these are three non-genuine, that's the name that you'll find in Hertzberg, vibrational modes. But if we attach this thing to something in a laboratory and make it very weak springs, then these would be vibrations too. They'd just be very slow, however slow. So this one just moves, translates rigidly up and down. This one translates rigidly back and forth. And this one just rotates and then very lazily rotates back together. The really high frequency one is this. This is the highest frequency one. It's stretching every part of the spring system. And these are stretching it too. This is one which will animate that makes the kite-like shape. And this is a weird one where it ends up with one thing pointing toward the other while the other one runs away from that. And then this one does kind of the reverse, you see. So basically these are modes that correspond to X motion globally, and these are modes that correspond to Y motion globally, okay? And this is the same thing down here as far as the global symmetry goes. But local symmetry, gone. It's 50-50 mixed. So this is a pretty good example of the contra situation to what you would have with those potential wells and weak tunneling. Okay, probably wouldn't hurt to go ahead and try some animations of these things. You can click on any one of these. Now all these things do is, I think, give you different angles for the connector springs.
Yeah, it's weak.
We would probably
There's one time that needs to spin on that.
I'll go with one that has 60 degrees just for the heck of it, see what that does. And once again, we're wondering why we didn't
Try your other laptop.
We'll try it on
It
this
looked
one.
like it tried to start making an internet
Yeah, that's
connection.
weird. I figured we were past those
Yeah, I thought so too.
things. Let's go see what this laptop has to say.
Yeah, those are old style links. No, they're good.
No, these are. I checked that.
Yeah, well, I changed the color of the
Yeah, let's see
underline.
how
There's
she
a
goes
clue
here.
to whether it was
There we go.
updated or not.
Okay, now I only have to do this once. This corresponds to this mode right here. You can see I've got the phaser there. And when you fool around with this thing, of course, you can just turn the phaser yourself or bring it so that it's right on the thing. It doesn't move much at all, okay? But when you get tired of looking at this libration, then you go ahead and just zero the amps, okay? And let's try one of these guys right here, okay? Well, that's translation mostly, okay? It's not quite straight up and down, you see, because we've got a good interaction between the springs that are holding this trampoline and this the ones that are connecting the object itself. So I'll zero that one out, and let's just take a look at this one. It should be translation more or less in the X direction, but not quite in the X direction because of the way these springs are connected. So it has a different frequency than the other one. Now, if I'll come back to these and make the holding springs very small in just a bit here, but let's zero out again and take a look at the ones that have some more nearly what the molecule would do. This would be a vibration that has X translation, sort of, and no Y translation. And then the opposite one here, this is anti-symmetric, globally symmetric, locally, if you could believe that, and it's of course not true for this particular connection here, but let's go ahead and run it anyway, and there you'll see what it does. Okay, so there it's doing that sort of kite motion. on the average, it's pretty much vertical motion, but not perfectly vertical because the outside connecting springs are at work.
Can you combine two of them?
And if you do two of them with the same frequency, you'll just get something that goes in a loop like that. If you have them phased thing. If I do two of them in phase, okay, let me try to do that. Okay, there's two that have about the same phase. Maybe I need to get down here a little ways, right? There they are. I get two, I would, if I did it perfectly, get two flat ellipses, right? And then if I set them at right angles to each other,
Oh, when you say flat, you mean flat parallel to the horizontal axis, right?
there,
No, that there's no interior to the figure that's traced out. It's degenerate ellipse. Linear. Like
you see
they're
this,
linear versus circular.
this one has a pretty strong connecting springs in addition to the springs that connect the atoms themselves. So it's got rubber bands holding it like a trampoline. So that's a, anyway, these are neat things to play with, and then of course you can change the constants on them just by pausing here and going to local control.
Or you can right click. Context menu. Will
Oh, and
expose
bring
the
a context.
constants.
Here I'll take the mount springs down to some small value here. I'll leave the nearest neighbor, which is the only thing that was turned on there. Nearest neighbor connections.
So give it
this-
something.
And I'll give it a some small amount.
It'll keep it from crashing.
Yeah, keep it from crashing. Yeah,
But you just
exactly.
have to choose a different
As
mode
it
if
runs
it's-
off the thing.
Right.
So let's go ahead and launch that. Okay, now if I do this guy right here, it will rotate, but then come to the end and come back. Okay, so the outside springs are not having much of an effect for any of these modes right here. So zero that one out. Let's see if translation works the same way. And there you go. Very lazy translation. Okay, so this is kind of like a molecule that's being held in an electric trap. The trap has a very flat bottom. Okay, so those are the zero frequency non-genuine modes. The modes we're interested in are these guys right here that actually vibrate. Okay, I accidentally hit a button there, so we'll let's say done here. I gotta zero everything here. Start over again and erase. Okay, let me
Click inside the canvas once
here.
to disengage it.
Yeah. Okay. Good. I'll go return here. I've forgotten about all of that. Okay, so here is a typical
Doesn't mess up very often.
mode. Let's erase so that you can see where the tracks are. And it looks like I've added another one to it already, so let me get rid of that. Erase again, and now we get a better picture of what this thing does. Okay. So this is very much like the modes that we're talking about here. This one right here is what we're looking at. Pretty weird. Okay. And all of these links lead to something like this. It's
the-
just a
the
question
links-
of what the spring holders are.
Sorry.
What angle.
It's the links thereafter that you won't see here that's already posted that'll take you straight to the pure mode oscillation. So it kind of supports the discussion.
Yeah.
It'll be there when you look at home. It kind of
Okay, let me, just to keep you from getting dizzy, let me zero the amps on that one. Okay, I'm going forward on this guy right here. So I'd say these are mixed modes, very much so. Now, if you have these guys, then you're forced to have circular modes. Basically, this is where you have the imaginary guy, but all of these zero. They can't be there if you're going to make a local symmetry that's C3 and doesn't have any bumps in it. Now you're going to get current carrying motion from that, and that's indeed what we see. There's the energies associated with those. They'll be doublets separated by some frequency. So you get an x plus iy and an x minus iy. That's what we call circular polarization when we did the C-type motion. So the other stuff is A and B-type motion. This is the C. And I won't bother certainly, but well, maybe we can get one of them to work. I'll go ahead on the thing and get back to the lecture here, move up to these guys, and see if we can get one of them to run on the thing here. So I'll just hit the second one, which is what we did. And there's the scalar breathing mode, which is the high frequency guy. Let's zero that out and turn on the next highest ones. Let's try this one right here with this one right here. And I'm going to put that at right angles so that I emphasize x plus iy, or y plus ix. It's not quite there. That's pretty close right there. Okay. So these are ones that we ought to, as you said, make initial condition ready so that you can show that stuff, fairly easily. And that's the kind of motion. And this is important too, because this is the motion that will be generated if this molecule actually is rotating in a plane, say, then you would get these two components, left and right circular polarization modes going there. Okay, and that's an eigenstate. Pretty neat. All right. Let's go back here to the lecture and go forward. Now, the rest of this is fairly mathematical. I'm just giving you some rote procedures that we'll be doing a lot of later on. But it basically just amounts to looking at the characters of two symmetries. The group, in this case, is D3 for the molecules that we're looking at. And then we can either subduce this the representations to those of C2, odd and even, 0 mod 2 even, 1 mod 2, binary bit 1 versus bit 0 is anti-symmetric. And then see how that connects if I were to reduce myself to a lower symmetry. That is, if I were to take the 6 matrices of the DE, or the 6 one-dimensional matrices of the A2, same thing for the A1, and just throw away the matrices that don't belong to either the identity or I3. Those are kind of small there, so that's why I'm pointing them out. So this is the group that just consists of doing nothing, and then there's one operator that does something in the C2 group, as you recall. It's the smallest group that has actually got a little bit of structure to it. And it has the irreducible representations of symmetry and anti-symmetry. So the question is, how does this representation look in the eyes of C2? And C2 isn't going to look at anything except this column and this column right here. And only one element here, the I3 element. So I come down here and I see 1 and 1, so I know right away that this A1 belongs to 0 mod 2. Okay? we've done this sort of already once or twice, so I'm just going through it again. Then I look at this one. How does the D3 representation A2 match up to the representations of C2? And we look here and we see a 1 and a -1. Aha, this one belongs entirely to 1 mod 2 in the C2 world. Okay, so we put a 1 here underneath 1 mod 2. This is a correlation table from high symmetry to low symmetry. Okay, the only one that presents a little bit of difficulty is how do I add these two up to make this thing here, 2 and 0. You add them. 1 plus 1 is 2, and 1 minus 1 is 0, so that means I have this one and this one inside of the E if I reduce my symmetry to just those two classes, in particular to one element of the second class, so that's why I have a 1 and a 1. Is that clear? At least, these are just a rote way. This is the simplest example of doing a correlation between call it a supergroup if you want, and a subgroup. Okay? You look up the characters for each of them and match them. Okay? Now that's a process that we're calling, this is a mathematical thing, subduce. That's what the mathematician says. You've subduced the representation. This irreducible representation is now reduced because we've thrown away, made illegal all of the elements except those of the subgroup C2. All right? So that's what has happened. Now remember, this is what happened when we built the irreducible representations of the thing. We took the projectors that belong to the class, the all-commuting projectors that commuted with everything in the group, everything in the algebra of the group. Okay, so these, this, and this were idempotent projectors. And then we took the projectors of the subgroup, that is, the projectors that go with 0 mod 2 and 1 mod 2, and tried them out on each of these projectors to see what we were going to get. And when we tried this one out, we got exactly what this table tells you. And then when we tried this one out, we got this number right here. So we got A2 there. So that's written mathematically as saying I took the representation of this big group, reduced the group by throwing away all but the C2 elements, and what I ended up was the representation O2, 0 mod 2, of the group C2. I ended up with that. Okay? So this is just a restatement of what this table displays so concisely. Same thing with A2. But then this one right here actually split the projector into two things: symmetry, symmetry, anti, globally and locally. Okay, local being the right-hand index and that. So those are the two idempotents that came out of that character, all-commuting idempotent. And so when I did a subduction to C2 of that one, I drew a little circle cross to indicate that this matrix subduced. That is, it became a direct sum of two representations of the smaller group C2. And the key concept for the physics is that projector splitting means level splitting. That is, this is telling you that if you have an E1 level in a degenerate E1 level in a D3 situation, and somebody comes along with some electric field or something and messes that symmetry down to a C2, you're going to split. This would be a stark splitting. You see, and that's the character table, or the correlation table is set up to tell you that these two are going to be different energies. They're not going to be degenerate any longer if D3 symmetry goes bonkers. Okay? So that's the basic idea of doing this subduction. And if you decide you want to go to C3, that was the other possibility, splitting the projector, right? Remember that? Okay. Well, what are we going to get here? Particularly, what is this thing going to split into? Because now we have 0 mod 3, 1 mod 3, and 2 mod 3. How are we going to get, and the only thing that's left here after we've reduced the symmetry are the R operators. And those are in this class. So this is out now. Whereas before we took out everything that was in the R class. Now we're keeping the R class, throwing that one away, okay? So you see I got a 1-1 for this one and a 1-1 for this one. You see, so all I'm going to get is 1-1s from these two, but this one's going to give me both of these complex representations. If I add that, I get 2. If I add this thing right here, I get the minus 1. That's what I get. Minus a half, really. Minus a half plus minus a half becomes minus 1. Okay? And then these two right here cancel I'm sorry. This is not be discussed at all. Okay? So that's just the answer right there. I'm going to be getting these two guys here when I do that, but for this one, I'm going to get a slightly different correlation table. That is, I'll get 1 sub 3, 1 mod 3, and 2 mod 3 for E. These guys, they come out the same. They distinguish each other. Okay? So this is 2 examples of going down in symmetry. And the correlation table, read this way, is always big groups representations here, the little groups representations up here. Okay, now the thing that we're going to introduce today, and this is a funny way to do it. I mean, this is very sort of seat of the pants, hand waving, not rigorous. We're going to make this rigorous with projection algebra later on, but this is a very important dichotomy of symmetry breaking. This kind of symmetry breaking that we've just been diagramming with this table read this way is applied symmetry breaking. This is where you come in and you put some fields on the system that breaks the symmetry. This kind of stuff is really weird. The stuff that's going to come out of the bottom of this by reading these tables backward. This is very, I shouldn't have pointed to that and called it weird. That's what most people think of as symmetry breaking. But when the system does the symmetry breaking to itself, that's called spontaneous symmetry breaking. And that is weird, because that's basically appealing to some sort of quantum mechanics usually. What we're talking about is somehow the symmetric system has a whole bunch of equal possibilities, and it just picks one. And just sits there. It's like taking a measurement. That's what this breaking of symmetry is that we're talking about, or about to talk to. Okay? And you read these tables backwards, and you get that. That's what we're going to see. We're going to see that if you take a C2 symmetric system, 2 equal wells, and up it to D3, you get a sum of E1 and A of the big group. And if you do this one, you get a sum of A2 and E of the big group. Okay, so symmetric, anti-symmetric, they're going to make, in a magical process called spontaneous symmetry breaking, these cluster states. That's what they're doing. They're putting levels together in clusters. So when you go this way in the table, the degeneracies go down. When you go this way in the table, the degeneracies, or near degeneracies, go up. And that is the thing. Now this one right here has to also be treated, but this is the one we're going to be talking about the most today as we finish up here. So we're going to be seeing combinations of A1 and A2, for example. And then we're going to see that sometimes when you do it, you just get one. Okay, so it didn't really go up at all in that example. But over here, yes it did. I got 2 things coming out of this one, and then I got slightly different 2 things coming out of that one. So this is, I just want to get clear the secretarial work that's involved. This correlation table is powerful because it does 2 things. The way most people would be used to it is going this way. What people are not used to go in the physics world is going this way. So don't feel that you're stupid because you don't see what that one is, but that's the thing we need to make clear over the next few lectures.
Dr. Harter?
How do you get more degeneracy when the system goes to sleep? That's kind of what it comes down to. Okay, so let's take some looks. Now this is an elegant mathematical section. It just says, when talking about the big group, irreducible representation will contain a little representation some number of times. And this big group, this representation may be obtained this way. If that's the case, then that number is the number of these little guys that come out of that particular representation. So we're going to make a lot of use. That's just saying there is a correlation table that can be read backwards. And we've already seen one when we reduce any group to no symmetry at all. 0 mod 1 equals 1 mod 1. That's just, this isn't binary, this is monary, right? A computer that doesn't work, okay? And when you do that with D3, you get a singlet, and a double, right? So this is the ultimate induced representation for any group, is to have all of the representations, each one of them, the number of times it appears is equal to its dimension. And this is what we were talking about, just the C2 and C3. So I throw in C1, the group that isn't even worthy of the name group. Okay, now we're going to see this at work in the reduction from full hexagonal symmetry. Well, we'll be satisfied just to do D6, but we easily get this. As you'll see, this comes very easily by taking a product of the D3 with C2. Okay, so the D3, as we already know, has a subgroup C2. It also has a subgroup C3. So that's what those two lines indicate. Now, D3 is a very nice normal subgroup of D6. And normal will be a definition we'll get used to. And of course, D6 has C6 as a subgroup. We'll look a little bit at that. Okay, so this is the slide rule for D6. And probably wouldn't hurt if I go ahead and show pictures of the operations that go with this. And it's probably not good to use that slide right, this machine right here, because it has problems with contrast. So I will back this one up to the slide rules and bring this one forward to the actual picture of a potential in a plane that contains symmetry D6. Now the question is, how do you make D6? I've already said that it's defined as the outer product of D3 with C2. Now you can only do an outer product if every one of the elements in here commutes with every one of the elements in here. Sound familiar for a local global business, right? There has to be that criterion that these don't have to commute with each other, neither do these, but they do in this case. Every one of these has to commute with these. And the reason that works is because all of the operations that we're talking about here that are in that plane, okay, rotations in that plane, all of these things are 180-degree rotations. And these 180-degree rotations are all perpendicular to the main axis rotation of 180 degrees. Guaranteed commuting of this with that. Then it's a question about, do you also commute with these guys here? Well, yes you are, because these are on the main axis, and so is this.
Okay, Dr. Harden,
Yeah.
I have a question. So, all elements in D3 commute with, so that's D3, like 1, R, 2, I2, I.
Yeah, let me
I1,
point
I2,
out.
I3, right?
Let me point out D3's axes. The I3 axis, okay. Then at 60 degrees to that is I2 axis, okay, and then the I1 axis. So these are axes around the face of this hexagon, right?
Yeah.
D6 includes, besides those, the 180-degree rotations around the vertices, the corners. they're J's. Okay? So that's what's new here,
Okay, but my
is
question.
making the J's.
Okay, so but you said all those elements commutes.
All of these, each one of these,
Uh-huh.
commutes with that one.
Okay, so D6 is an abelian group.
No, because this is not abelian. And once you, if you have a group in an outer product that's not abelian, that outer product is not abelian. This is an abelian group, I will grant you. But if I wanted to outer product this thing with 90-degree rotations around Z, I'd still be able to do it.
That's a dumb
Yeah.
assumption.
Yes.
Oh my God, what a... Oh,
think
Jesus
consciously
Christ.
class.
Sorry about that. Yeah,
Yeah.
I thought
Yeah,
it was
don't
based on
forget
that
that
part.
D3 is our first example of a non-abelian,
I was
right?
thinking just the isomorphic part of it. So D6 is isomorphic to that, obviously.
Yes.
Oh my God, I cannot believe that I have asked that question. Yeah.
And this is
honestly,
something you may have
confuse-
learned before in a group theory.
Yeah. I
class.
learned it in a group
Yeah.
theory class, but
Yeah. This,
It'll
oh
really
my
stick.
God.
it's one of those
Yeah,
things
I'll
where they
never
say
forget
it's
that.
well known, but with all kinds of well-knownness, right, which very often slips you by. Yeah. Okay, so here's what we do,
Honestly, it's
you
not
see,
easy.
is we take each one of these guys and multiply it by 1, okay? So that turns out to be, and that's the thing that's important here, is that I'm taking 120-degree rotations here, and I'm attaching to them an extra 180. When I pile them all up, I get to have, because of this guy multiplying that guy, okay, I get to have this guy, which is 180 degree, but I also get to get a 60-degree rotation out of the collection of things. So this right here is a symmetry now of D6, no question about that, but that's the way you get it. And you can see I'm writing the products here. I'm writing the products of, well, 1 times RZ, big deal. RZ is 180-degree rotation, right? So that's H cubed, H being a 60-degree rotation. 60 times 3 is 180. So H cubed is this one, 180, okay? That's a new guy. We didn't have 180-degree symmetry for D3, but we do for D6. Okay, so that's really important step right there. Then I take 120 degrees rotation, add or subtract from RZ's 180. Okay, I get H5. H5 is all the way around except for the 60 degrees right here. Okay? And so forth. Each one of these H comes out with a minus 120 times 180. That gives me a nice an H element. The H element is this guy right here, 60. Okay? And then the rest of these guys, these are perpendicular to the main axis, okay? But that commutes. This is 180, this is 180. When they're perpendicular to each other, it's like the 180 degree D2 operations that we talked about. They're all orthogonal to each other, so they commute. All of these commute with each other. Let's see if that's right. This one, I1 RZ, okay, that's J1. That does not commute with J2 or with J3 because of these guys, but it makes them, and then you're finished. You've got, if you put these things all in a table now, you're going to have all of the 180 degree rotations of the original D3 plus another 3 for the hexagonal. Now there is one thing to be worried about here that sometimes stops students. When we do an I or a J, we mean to flip the molecule, but we do not flip the potential plot. The potential plot is a separate thing. It's just giving you energy up versus angle, okay? So the electrostatic potential doesn't care which way is up. And these wells remain wells, and barriers remain barriers under all of these operations. I just wanted to make that clear, because that actual object, the way it's drawn, does not have the ability to be turned over. Everything would fall out, right? I mean that plot to be stick to the thing. The rest of the molecule can turn over. It's flat.
So if I say D4, I direct,
D4.
If I do D4 direct product with C2, can I get D8?
You can do it if you do, you get D4H if you do reflection symmetry with it. You got to watch it for the C4s, because C3 cross C2, and I'm going to mention that just very shortly here, is exactly C6.
C3, C2,
But C4 cross C2 is a different group from C8.
Huh.
The reason for that is that 4 and 2 are not relatively prime. Whereas here with 3 and 2, they are relatively prime. And you're probably remembering some other stuff from the group theory, that in order to get a, you have to have relatively prime numbers in order to get a new group.
Yeah,
Right?
clearly remember
Yeah.
that theory now.
I should say avoid getting a new group. And that's what we've
Yeah.
got here. 3 and 2 are relatively
And
prime.
it will equal, so if they're
Yeah.
relatively prime, I know because I have done it for the integers, like when you have like a
Mhm.
class of integers.
Mm-hmm.
So if the, I guess,
Well, we've done it before when we did the table of group up to 64 order. And you noticed how many abelian groups there were. If you go through there and look at what the black ones were, there were a heck of a lot of them in the 8 column, right?
okay,
Because you could make C8, and that's different from C4 cross C2, because C4 cross C2 doesn't have anything with order higher than 4. And then finally, there's C2 cross C2 cross C2, right?
so
All of those are of order 8, but very different. The
So
C2
the
cross
only
C2
way-
cross C2 only has order 2.
the only way I can get D8 is like something like C8 or
Mhm.
C1,
Mm-hmm.
because those are like the only known,
Yeah.
the only relative primes that
Yeah.
can form that higher order group, right?
That's
D8.
right.
Okay.
It's-
Oh.
It's got too many 2s in it, right?
Yeah.
Right? Got 3
I
2s
see.
in it. Yeah. Okay, so remember that C2 cross C2 is not C4, right? It's this thing, right? C4's got complex numbers here, right? I and minus I. You can see just from the representation theory that they're not the same. But C4 has order 4 elements. This thing doesn't have anything but order 2 elements. Order meaning how many times you have to multiply before you go back to 1, right? So there's our old friend D2 with a character table of C2 repeated 3 times with a positive and then once with a negative. We're going to do the same thing with these two guys, C2 cross C3, and you can link these up if you want to see what else we have to say about these. This one is a little tricky because when you do this one, by putting this character table with 1 here, and then this character table with this one here, and then this whole character table with this one here, and then finally you take this character table with a minus, see all the minuses? You're done. That is the C6 character table. But what's kind of weird is the even guys are the ones that are lined up here, and the odd ones are down here. And that's something you ought to go ahead and just make sure that you understand why that's true. Because when we gave this character table in that link, we just went 0 mod 6, 1 mod 6, 2 mod 6, 3 mod 6, 4 mod 6, and 5 mod 6. Only this one and this one would have been right. Okay, this is the order you get when you pull this cross product stuff off. Okay, so that's what we're really dealing with. Because those are both subgroups, and this is a subgroup of D6. It's half of D6. D6 has 12 elements, and this is half of them. Okay? So that's something I wanted to make very clear. But now, the thing to point out is that when we take D3, okay, character table, this guy right here, put it with 1, that's this. Take the character table, put it with a 1, that's this. I'll do it one more time now. The character table with that one is this, okay? And then finally, with the minus, is this. Bingo, our character table. But you have to be careful how you label it. It goes A1, A2. It does not go then B2 and B1 or anything like that. You got an E right away. And it's the second E, not the first. The first doesn't come until the bottom. So this one is like a vector, that one's like a tensor. So, you know, it's good to know this group because it's just, once you've seen this transformation of two groups into a big one, it's very simple. Here is the elements that belong to the D3. Here are the extra elements that make it D6. Then all you have to do is get used to the weird notation. And I've got mnemonics for that. I've probably already told you that whenever you see the letters A and B, A means always the same, and B means back and forth. So the back and forth, the odd guys are down here. And by back and forth, I mean that they both have a minus sign with respect to the 180 degree rotation. That is H, which is the 60, and 3 times that is 180 degrees rotation, is giving you a minus sign for both of those and a plus sign for both of those. For this one, it has both. For this one, it has both.
Dr. Harter?
Yeah.
D3.
That just takes care of the A's and the B's. Then there's these sub-indices here. Okay?
Yeah.
That's determined by the Y rotation. This one's determined by the hex rotation, these A's and B's. This one's determined by the Y rotation, the flip, J3. J3 is the one that determines that. That's this guy right here.
Dr.
You
Harter?
gotta pick one, right? So we pick J3.
In general, D3 direct product C2C doesn't equal C2C direct product D3, right?
Say that again.
So,
D3
well, I will
outer
use
product
it.
C2
Uh-huh.
gives you D6.
Uh-huh. What if you have C2 direct products D3?
Change the order.
D3 cross C2, D3 cross C2. That's what I want. I want this guy, then this guy. So I'm putting this table over that number 1. Then again, that's this number 1 going on the right, okay, and then minus 1 going on the right.
Yeah. So
Is that right?
My question is, so if I have like a group A, and then I direct product another
Mhm.
group B,
Yeah.
that doesn't equal if I take the product B and I direct product the A, right?
Yeah.
That-
It's like this is the little India and this is the big India, right? This is the number that determines the number on the right, okay? See, if the other way to do it would be take this guy and put it on top of that one, right?
Yeah.
Then put it on top of that one, then put it on top of that one. Do the same thing. You'd get a very different ordering, but it would all be the same numbers because you would have accomplished all possible products. The name of that is Cartesian product, right? And you don't get exactly the same arrangement when you flip them.
That's what I asked.
Yeah, that would be a different arrangement. This is a much, I think, cleaner way to do it instead of having a whole bunch of little 2x2s.
So if I change that arrangement, I will have to change my algebra, right?
You'd have to change these guys. You'd probably get A1 and B2, then you'd get A2 and B1, and then you'd get E2 and E1 for the third, whatever you want to call it, trimester. If you'd have 3. See, there's 3 rows here of 2s, right? instead of 2 rows of 3, right? Other than that, the numbers would all be the same, they'd just be rearranged. Okay, so be aware of the J flip, or any of these flips, each of these, the J's flip, 1, 2, or 3, okay? For 1, it's positive. For 2, it's negative. And then the B's do the same thing. A negative here for the 2, and a positive for the 1. So you get a reversal. Instead of going A1, A2, this one goes B2, B1. We'll see that in our band structure in just in a minute here. So it all seems like very trivial accounting, but it is important to nature to do this counting. It is very cognizant of where its phases go negative or positive, and it makes a big deal. These are the actual matrices. You can also get all of them. The irreducible representations that we've already gotten for D3 just appear. And that includes these guys that are 1 and -1 for A1 and A2, or the other way around, -1 and 1 for B2 and B1. The E's, this is a vector, that's a tensor. This vector goes negative to these numbers on the right-hand side. These are identical numbers to these. So that's one little point that you should notice, is that this matrix has turned negative here. It didn't turn negative up here. And the same is true of each one of these in turn. And that takes care of all of the symmetry that you need for the hexagonal system that we're going to be looking at, the modes for that. So this is the next step, as it will, as you were. We've just doubled the D3 problem into a problem. Now, the correlation tables between the D6 and the C2 and the D6 and the C6, these are analogous to what we had before, which was D3 correlated. And I have not told you what this symbol means. It means it's the group theoretical greater than, right? Greater than is just that, right? The great side is on this side, right? And small on this side. Well, the same thing with this. This just means this is big enough to contain this, and in fact does contain it. If you turn it around so it's a C, right, you can't say that that thing contains that. That doesn't work. That's a mnemonic that won't work. Okay, so be aware of that. This is the little guy, that's the big guy, and it's a greater than symbol. Anyway, this is where I'm asking you to take the representations of D6 that we've just made here and see how they behave if I throw away all of the group, the half of the group that is not C6. And then here I ask you to do even a more deadly job. I want you to throw out everything except the J3 and the unit. So I just have odd and even with respect to J3. Okay? Well, our characters or our representations tell us that A1 is even, A2 to odd. Okay? Then E's got both of them, and that's the second E. The first E, the vector, the tensor, they both have both the odd and even in them. Then comes the B's, okay? Well, the B1, 1 means it's got the even. 2, remember, is the odd, according to this flip labeling, plus and minus, respectively, for 1 and 2, even and odd, respectively. Okay. All right. Well, we're going to read these tables backwards too. This one right here, of course, is very obvious for the A's, and then the B's, they're very obviously the odd in the six-fold world. And then the E's come up with the even values, 2, 6, and 4 mod 6, whereas the first E1 comes up with 1 and -1 mod 6. This one, the tensor, comes up with 2 and -2 mod 6. So that's the correlation in a nutshell for D6 to C6. And we're going to read that backwards to make our band theory. The band theory is given very nicely by doing that for two cases. The cases where C6 local symmetry is in effect, or C2 local symmetry is in effect. So that's what we should get to here while we still have time. Now this is a page out of the Principles of Symmetry, Dynamics, and Spectroscopy. And this is chapter 3, page 50, and that link should work. And just go there. I'm afraid to try it here because...
Oh, it won't work there because it's not underlined. That's a mnemonic clue.
I think that from the book it's actually page 199.
Yeah, except that you have to give
You're
the
on the
page
wrong
numbers in
markup.
PDF paging, and that's what I do when this thing works.
It looks like it's there, it just failed to make the internet. So there is a hidden link there, it's just...
Yeah, we're going to have to figure out what that is.
Well, like I said in the latest version, all those are well defined with magenta underlines, so you can tell a mile away that it's linkable.
I wish it was a way to, let's see what this one does here. Bingo.
That's the... Yeah.
And of course, the problem is that this was scanned in, so in order to fit it, I had to turn on the side, so big deal, okay? So that is a fly that we'll probably take out of the ointment when we rescan. But anyway, what you're seeing here for the D6 is an ordering that goes like this: A1, first E1, second E, that's E2, and then these guys right here, B1 and B2, the B mnemonic, that's the first Brillouin band gap that will occur when you're running waves of various angular momentum up to momentum 6 to 7, 8, 9, okay, on top of a very weak potential, very weak periodic potential. Then, actually, that's a big exaggeration. The B1 and the B2 will be just a tiny splitting. It'll be like the degeneracies that you've got here with the two pieces of the E2, or the two pieces, but that's solid, that degeneracy of the cosine and the sine of angular momentum 1 and angular momentum 2, that's solidly degenerate. But then the 3 can resonate, you see, with the 6, so you get a splitting here, a band Brillouin gap, and it's going to be small. And then you'll get the E2 and then the E1. They're backwards. Okay, it's because of the mod. You're doing everything mod 6 and coming now down. So you get the E2 first and then the E1, and then finally an A2 that's going to match up with an A1, and then that's all going to start over again, just like the ordering that we see here. As you go up to 7, 8, 9, 10, 11, 12. So we go up to 6. We end with A2. Okay, so that's when the global symmetry, D6 to C6, global symmetry rules are in effect. Over here, we get these huge barriers, okay? And these guys are down at the bottom of this thing, and they're just stuck in there, and there's practically no wave function in between because the potential is so high, okay? So for all of these, local symmetry is going to be in effect. And we're going to all have, with this particular set right here, local symmetry. And for all of these, we're going to have local anti-symmetry. But then we're going to have a certain number of B1s and E2s and E1s and A1s in some arrangement. And that's where the anti-correlation, the correlation of looking at columns, becomes effective because you see deep in the barriers, it's just local symmetry. All I can see is two walls. And you've got a huge brilliant band gap here between B1 and B2. And then just tiny splittings for these guys. So those are the extremes in band theory of this type, of this one-dimensional type. But it's something that goes for three-dimensional lattice mechanics as well. It's just a bit more complicated than this. Same basic idea. So this is the actual picture of the waves. And here is the correlation table that goes with the global C6, with the local C2 symmetry that's in effect for this particular picture where we have really tall barriers and all the waves are crushed into exponentials. And so these barriers aren't that high. They're kind of like what's on the screen down there. But anyway, this is the D6 greater than C2 correlation table. C2 even and odd. And there you see it, A1, then A2, then E2, B2, B1, and E1. Okay, so we're seeing those particular things. Here's A1, E1, E2, B1, then comes B2 with a huge gap between the Brillouin band boundaries. That's the way I remember the B goes there. And then it counts backwards. E2, followed by E1, followed by A2. So this is the simplest example that's not really quite trivial. Now when the barrier is low, okay, if I could lower this back down again so that it's more like that, the picture on the left over there, then this is what you use. A1 and A2 are pretty close together. E2 comes when it comes, and then B1 and B2 are real close together there at the first band gap, and this is the second band gap. So that's kind of what I want to get. Now, the point of this, as far as spontaneous symmetry breaking, is that these barriers get really high, and you put some noise on this system, the wave function collapses into one of them. In other words, this is a potential measuring device. Where was the wave? They're all equivalent, so you're going to get a count here maybe, and then a little later you're going to count there, and then you're going to get a count here. And bam, 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 you add them all up and you get the same number of counts pretty much in those wells for a distribution of waves. But each time you force the wave to, in some sense, collapse. In other words, we're talking about, when we do this reverse engineering of the correlation, we're talking about wave function collapse, really. That's the word spontaneous being used. And that's very mysterious. That is very mysterious physics right there. But at this level, it's just arithmetic, group arithmetic.
A spontaneous collapse of the wave.
Here's D4. If you want, remember I always tell you to do D4. Do the correlations and everything for this. This is also in the principle. It's taken. This is directly a copy of the thing. Same thing. High above, low barriers. D4 global symmetry rules. Okay, so we get the doublets that we're used to, but also some things that are nearly doublets that are at Brillouin band gap. So this is the simplest one. D3 is too simple because we don't get this. There's no B representations for odd groups. Oh, we only have to wait till we get way up there with D3 before we get two singlets. Because it only has A1, A2, right? And one kind of E. This one only has one kind of E also, but it's got these B's. And then you get a large gap right here, and you get these guys showing. Okay, we're getting real close to having to quit here and go to the seminar. So I can show you a couple of these animations. Certainly if I go over to this screen, and we can take a look at some of the ones that, and these will be ones that are pretty much doing local symmetry stuff. So let's see if I can get one of these going here. Yeah, there's a good one. And you can tell it's local symmetry because I've got this little, very nearly degenerate set on the low part here, and I get, remember this is upside down, this is deep into the high energy but low tunneling, if you were calling that coupling tunneling sets, okay? So here we're looking at this particular mode, and I will go ahead on this screen so I can point at it. This one's got local symmetry, that means radial motion, and it's got global symmetry as well. That is, when I look at a J3 flip, I see that it's symmetric. Those guys are symmetric, not anti-symmetric. Okay. Now, right next door to it is one that's got a global anti-symmetric wave. So I might as well zero the amps and we'll go try for that one after erasing. Okay, I'm going to try this one. And one of the things that you'll notice is where it's, these guys hardly move, and they actually shouldn't move much at all, but there is a little bit of coupling in the outside world, so you can expect a little bit of motion on the clash points. Remember, we're global symmetry and local anti-symmetry. Actually, it's the other way around. It's local symmetry, but global anti-symmetry, right?
Mm-hmm.
So you can see these two are opposed to each other. This one's in while that one's out, vice versa. Okay, so this is an example of that effect. And there's another one waiting right here. It's just the opposite. Now it has global anti-symmetry, but local symmetry. See, that's kind of like this one. I wonder if that's, that may be a labeling problem right there.
Okay.
Let's see, this is 1, 1, 0, 1.
All right, is it? I
1,
just
1.
counted, first counted in order.
Yeah. Let's just see what it looks like. I'll zero it out here and see what it does. Indeed, the guys that are on the J3 plane don't move. That's the local symmetry for all of these guys is even, whereas, let's zero the amps and go down here, the local symmetry is all odd. For example, let's do this one right here, and you see their angular motion. That's equivalent to being anti-symmetric in the local thing. And of course, we're trying to be globally symmetric here, and therefore we don't have anything, very much motion, right at that plane. So erase that one and go for one that, like this one right here, where we've got anti-symmetry locally and globally. And now you see the anti-symmetric motion. This guy zigs when that one zags and vice versa. And then we've got angular motion perpendicular to the radius everywhere. So that's local anti-symmetry. Anyway, these are available just by clicking and then fooling with the phasers. And you get both the energies and the splittings, the tunneling splittings of those that correspond to local symmetry being pretty well enforced, even though they are connected to the outside world, which is the way you lose your locality, right? So people that live in the middle of Arkansas or Mississippi, you see, the global effect, right, is not zero for most. And that's what's true here as well. Okay, well, so that's about it for this. We're going to be taking on the octahedral group and looking at its correlation, well, first its representations, but also the modes of something that has octahedral symmetry, and we have animations for that that you'll be studying as well. So I guess we'll just call it a cut, and then we've got to go see a supposedly very interesting seminar that's coming up in just 15 or 20 minutes.